Okay, so remember that we are talking about relative motion. And we're working on this example that we started last time. You have this hinge connected to a wall. And one member makes an angle of 30 degrees with the horizontal like this. And then the other member is horizontal at this instant. All of these things are just at a single snapshot. Remember, if these things are rotating, obviously in the next instant, these angles will all be different and stuff. So you're just doing this instant by instant. The lengths of both of these are 1 meter. And we had an angular velocity of this body of 10 radians per second, and an angular acceleration in the same direction of 5 radians per second squared. And then for the second body, we had an angular velocity of 8 radians per second and an angular acceleration in the opposite direction of 20 radians per second squared. And we're trying to calculate the acceleration of this point here. And so the way we're going to do this, I named these points G for the hinge connected to the wall, because that's not moving anywhere relative to the ground. So you can think of that as your ground. This is A, and then we're trying to calculate the acceleration of P. And so you can think of these as, this is 2 circular motions. You have this point A moving in a circular path like that, where G is at the center. Okay? And then you have this second circular motion that's this point P moving around A. Okay, so you have these 2 circular motions. And the solution is combining these 2 using the relative motion equations. So the acceleration of P relative to the ground is the acceleration of P relative to A plus the acceleration of A relative to G. And you know this is in the right order because P over G is equal to P over A times A over G. Okay? The first thing we calculated last time we got through the first half of this.
Quick question.
Yeah.
Is it always going to be like the lineage coming that we want mechanical?
Pretty much. It's hard to say always, but yes, pretty much. And the reason is no other point is, only points on this body are moving with these angular velocity and acceleration, So it doesn't do much good to try to do this point and this point, you know, because you don't know what the angular velocity and angular acceleration are.
And then the constraints, like if G to A comes with 30 degrees, that is irrelevant.
That is not relevant because this is just instant by instant. So even if this only had 2 millimeters that it could move, if it's in that 2 millimeters at this instant, that's all we care about. As far as we care, it can go all the way around. Yep, that's right. So yeah, things can definitely be in circular motion that don't have a full circle of range of motion. As long as at that instant it's moving along a part of a circle. Okay. Okay, so last time we calculated that the acceleration of P relative to A, so, no, we didn't do that. We calculated that the acceleration of A relative to G was negative 84.1, 54.330. And we did that using the watermelon equation. So the first thing we considered was the circle on the left. And now we're going to the circle on the right. So the acceleration of P relative to A is the angular acceleration of this body. So that's the 20 radians per second squared, cross with the r for that body, plus omega 2 cross quantity omega 2 cross r2. And let's just start figuring out what these different vectors are. Okay, so first let's figure out what alpha 2 is. Okay, so alpha 2, it says, is, you know, this is in the xy plane, the z-axis is coming out. Alpha 2, according to the right-hand rule, is in the positive z direction, okay, with a magnitude of 20. So this is 0, 0, 20. The units are radians per second squared. Now alpha 2, right-hand rule is going this way. Your thumb is into the page. So that's the negative z direction. So omega 2 is 0, 0, negative 8. And then we need that r vector. That goes from the center of the circular motion. Okay, remember, we're only considering this circular motion right now. We're not thinking about this right now. We're breaking it down into two simple motions. And so the r vector is from the center of the circle to the point we care about. That's 1 meter in the positive x direction. So that's just going to be 1, 0, 0 meters. Okay, and so the acceleration of P relative to A is 0, 0, 20 crossed with 1, 0, 0 plus 0, 0, negative 8 crossed with the quantity 0, 0, negative 8 cross 1, 0, 0. You can just plug this into your calculator to do it. This will come out to be 0, -8. Yeah, 0, -8, 0. And then this whole thing will be 6400. That should be the other way. That should be negative. Yeah. And then this one will come out to be 0, 20, 0. Okay, so altogether this comes out to be -64, 20, 0. What are the units here? Yep.
Meters per second squared.
Yep, we're in SI units, and this is a regular acceleration, so this is just meters per second squared. And so now put these two things together. The total acceleration of that point P, you can also think of that as the acceleration of P relative to G. Is -84.1 54.3 0 plus -64 20 0. So you get -148.1, right? 74.330. Yes.
Can you just add members and do this for?
Yes, exactly. Yep. So if you had 40 members all connected to the ends or whatever, you just keep going along. The way that you can think of it with, yeah, you can just add them all, and you can think of it as like we added these two to give us the acceleration of this point P, and now the next thing would be relative to P. So you add what you got from this to the next thing, then that's the motion of the next thing. Yeah, so that's exactly how it works. Any other questions about this? Okay. Before I give you one to work on, I want you to think about this for a second. So here's a point to understand. Let's say we have these two things, and they're free to swing relative to each other. And let's say we have an angular velocity of 10 radians per second and an angular acceleration here of 20 radians per second squared. And then for the second one, we have an angular velocity of 10 radians per second and an angular acceleration of 20 radians per second squared. What does this motion look like? Okay, so, notice both of those angular velocities are the same. It's 10 radians per second going clockwise. Both of those angular accelerations are the same. That's 20 radians per second squared counterclockwise.
Is it just reversing its position?
So yeah, that's kind of the question is like, really like the question comes down to this. This body is connected to this body. Are these angular velocity and accelerations telling you what that body is doing compared to this one? Okay, in which case, this would be opening, if it, like, think of it as like a jackknife, it would be opening more, but slowing down as it opens. Or are these values relative to the ground, in which case this thing would be maintaining a constant angle between them and just moving like this and slowing down. Okay. Do you understand the significance of that point and being able to describe this stuff with these values?
So what did we just do? In the example, was
Yeah.
it with the forces or acceleration on the second body was with respect to the first body?
Yeah, that's right.
But you can do it either way.
Well, that was a linear acceleration. We don't have any linear accelerations up here yet. We only have angular velocities and accelerations. So the question is, when you see a problem and angular velocity and angular accelerations are reported, are they being reported relative to what this thing's connected to, or are they being reported relative to the ground? Yep.
I mean, if the joint is able to move freely, they're both moving relative to the ground, right?
Yeah, that's right. Well, yes, they are. And I mean, there's nothing that says you couldn't report these relative to this body, but these values are always relative to the ground, okay? So this contraption here is rotating right now as if this was rigidly fixed and the whole thing was swinging this way, okay? These angular quantities are always reported relative to the ground. Okay?
And that's how they're calculated?
Yeah, that's right. I mean, that's just what the meanings of them are. And so don't look at this and think, I guess, ignore the angular accelerations for now. I just put them in there because those are also reported relative to the ground. But don't think of this as saying that this has an angular velocity this way, and since this has one relative to it, it's swinging this way and opening. Okay, that's what would happen if this was 10 radians per second in addition to what this is. But it's not additional. It's just saying both of them are moving with the same 10 radians per second. Okay?
Therefore, there'd be no movement at that point.
No movement at this hinge, it's like that's welded. Yep. The whole thing is just swinging.
So when those values are equal, you could really just draw a circle from your very end around G.
Yes, that's a very good observation. That's exactly right. If we noticed that these two values were the same, we could just notice that this is in circular motion around that point and do it. But I don't know. Yeah, if that happens, you can do that. But you also can use relative motion and you'll get the same thing. Yep. Was there another question?
Yeah, just if you look at if you set up the relative motion,
Yeah.
if you report it with respect to the one, then it would just be 0 and the term would drop out.
If you report it relative to, no, it wouldn't be 0. It would be like, you would calculate, want to do it?
Sure. No.
Okay, you don't have to. Everyone else is doing it though. Okay, so calculate the acceleration of P. We need angles for these. Let's call those 45. Let's call the lengths 2 meters for each. And we want to calculate the acceleration of P. Okay, so I guess I'll name them the same things I did before. I'll call this G, I'll call this A. And so the acceleration of P is the acceleration of P relative to A plus the acceleration of A relative to G. And after we do this, we'll just do it assuming, you know, like you were just saying, Colton, and we'll see that those answers are the same. Okay. Well, why don't you, so let's all do the same order. Let's calculate first the acceleration of A relative to G. Okay, so that's going to be the angular acceleration of the second body cross R for the second body, plus angular velocity of the second body cross angular velocity of the second cross R for the second. And I mean, just always start out by just figuring out what these are as vectors. Okay, so take a few minutes, see if you can do that. Like, work together, ask me if you get stuck, but see if you... So, for the second body, the lower body, the whole idea of this exercise is that alpha and omega are going to be the same for the two bodies. So this is going to be, alpha is going to be 0, 0, 20. Omega is going to be 0, 0, negative 10. And now R2 is going to be what I said it was before, 2 times the cosine of negative 45, sine of negative 45, 0, which is 1.414, negative 1.414, Omega is 0, 0, negative 10. And R is 0, negative 2.8280.